Hello everyone, my name is Kawtar Tifidat. I'm a PhD student. I'm working on electronics and renewable energies at the Laboratory of Materials, Signals, Systems and Physical Modeling at the Faculty of Sciences Ibn Zahar Agadir. So today I'm going to present our work which is about double diode based modeling for predicting photovoltaic modules electrical performance. This work is organized as follows. First, we will start with the problematic and objectives. Second, we have the research methodology. Then we have the results and discussion. And finally, we will close with a conclusion and perspectives. So let's start. As you can see here in the first figure, the world consumption of fossil fuels has been increasing more and more with the years, thing which involves several hidden problems such as the global warming, economical problems, health disasters, and geopolitical tensions. However, that pushes many countries to look for other sources of energy that can be renewable, clean, and safe, such as the solar energy, by employing the photovoltaic effect to create large PV stations containing a large number of PV generators or PV modules. These PV modules are made of PV cells connected in series and in parallel. Every single PV cell can be modeled using the double diode circuit model given here, and which is characterized by 7 unknown parameters. So the objective is to identify the values of these unknown parameters as to model the electrical behaviors of the PV generators. To this end, three kinds of approaches can be followed. First, here we have the analytical approaches, which are based on the resolution of analytical equations. Their major limitations are the use of approximations and tedious calculations. And second, here we have the numerical approaches using either the resolution of nonlinear equations numerically or fits the IV model to the experimental data. However, they are time-consuming and highly affected by the wrong initial values. Thus, in this work, we propose a hybrid method combining both approaches to benefit of their advantages. For this objective, in this work, the 7 parameters are divided into 2 groups. The first group contains the 4 parameters that are sensitive and hard to be initialized to be extracted analytically as functions of the 3 remaining parameters. The second group contains the remaining 3 parameters that will be extracted numerically using data fitting technique. So let's move to the details of the research methodology, and we start here by the analytical extraction of the 4 parameters IPH, IS1, IS2 and JP. So the procedure consists of the evaluation of the current equation at the 3 remarkable points of the IV curve to get the 3 first nonlinear equations of the equation 2. These equations link the 4 parameters, and to complete a system of 4 nonlinear equations, the fourth equation here corresponds to the derivative of the IV equation applied at the maximum power point. And here in the equation 1, we have simply some denotations that we have adopted to simplify the equations writing. After getting the system of the 4 equations given in the equation 3 and by adopting the matrix denotations below, the equation 3 can be written as a matrix multiplication. The matrix multiplication is given here in the equation 4, and to solve this system and extract the theta vector regrouping the unknown parameters, we use the resolution of the equation 5, allowing the extraction of analytical expressions of IPH, IS1, IS2, and JP as functions of RS, N1, and N2. Then, to get the values of the three parameters N1, N2, and Rs, we minimize the squared error given in the equation 6, which is calculated between the measured and calculated currents using the Liebenberg-Merkot algorithm. Here we have the flowchart of the proposed method. We start by the input data, then initializations, and the numerical extraction of N1, N2, and Rs, and then the analytical extraction of IPH, IS1, IS2, and JP, and finally the calculation of the electrical characteristics, IV and PV curves. Now we move directly to the results and discussion session. To validate the accuracy of the proposed method, we apply to predict the electrical characteristics of polycrystalline and a thin film PV modules, for which the characteristic parameters values are given here in this table. And for the test of accuracy, we have selected the absolute error and the root mean squared error, and also the normalized root mean squared error as statistical indicators. Here we have the calculated values of the 7 electrical parameters for the two PV modules when using the proposed method compared with other methods of the literature. As you can see here, the proposed method corresponds to the best accuracy of prediction of the electrical characteristics by yielding the least values of the normalized root mean squared error when compared to the other methods of the literature for both PV modules. For the multicrystalline, you can see here that the value of the normalized root mean squared error is about 0.65%, and for the thin film is about 0.76%. The figures here show the calculated IV curves using the proposed method compared to the other methods of the literature, and also compared to the measured data for the two PV modules when operating under the standard test conditions. And the figures in B show the corresponding absolute errors to each method. As you can see, the predicted curves when using the proposed method match with high accuracy the experimental data, and especially at the vicinity of the maximum power point. Now, to switch from STCs to non-STCs, to switch from the standard test conditions to real weather conditions, we employ the transfer equations that we have here, and which allow the use of the STC values of the 7 parameters to compute their values at non-STCs, then to predict the electrical behaviors at non-STCs. The results are shown in these two figures. In A, we have the predicted IV characteristics for fixed temperature and different levels of irradiance for the multicrystalline. And also in A below, we have the corresponding root mean squared error to each modeling technique and each irradiance level. In figures B, we have the results for fixed irradiance level and varying backsurface temperature. And as you can see, the proposed approach matches the least values of error for the great majority of irradiance levels and the whole levels or whole values of temperature. Moving now to the conclusion and perspective session. And as to summarize, the PV stimulating method introduced in this work is based only on the values of the key points of the IV curve to extract the 7 parameters of the double diode model. The obvious parameters to be initialized are extracted numerically using the Liebenberg-Merkot algorithm, and the remaining parameters are calculated analytically without using any approximations. The results have shown a good accuracy compared to some of the most reviewed methods of the literature. Thus, this method can be used for dynamic applications and for PV designers requiring simple modeling techniques. For perspectives, this method can be applied to determine the real-time values of the 7 parameters for PV modules of various technologies operating outdoor in the real weather conditions. And that's all for this presentation. Thank you for your attention.